Hi everyone, I'm Ruiquan, a third-year PhD at Stanford. Today I'm going to talk about the hardness of Approximate Sperner and its applications to N-way-free K-cutting. This is based on my joint work with Mohammad, Aviad, and Amin. Aviad is my advisor, and Mohammad is a fourth-year PhD student advised by Aviad and Amin. The main focus of this talk is the complexity of the relaxation of the celebrated Sperner's lemma. I will first introduce the lemma and the relaxation in our consideration. Then I will talk about its application in N-way-free K-cutting and finally give some high-level ideas about our techniques. In Sperner's lemma, we are considering the so-called Sperner's coloring. In the coloring, we have an arbitrary triangulation of the standard K-simplex, and we color the points in the triangulation following two boundary conditions. The first one is that the K-simplexes of the entire K-simplex should be colored with different colors. For example, this is a triangulation of the two simplex. We color the vertices of the entire two simplex respectively by green, blue, and red, and so this satisfies the first condition. The second condition is that points on each facet are colored by one of the colors on its vertices. Let's see this candidate coloring for the point inside the triangulation. These 2 points violate the second condition. For example, the color green should not appear on the facet whose vertices are only colored by blue and red. So this is not a Sperner's coloring. To fix it, we can simply modify the colors of these 2 points to blue, and the figure on the right gives us a Sperner's coloring. Given any Sperner's coloring, the Sperner's lemma states that we can always have a small rainbow simplex that contains all the k+1 colors. In the earlier two-dimensional example, this gray triangle is a rainbow 2 simplex. This lemma has a lot of applications in mathematics and game theory. It is first introduced to give a combinatorial proof for the famous Brouwer's fixed point theorem in topology. Then many variants of fixed point theorems are proved, which lead to the existence theorem of Nash equilibrium and N-way-free K-cutting in game theory. Besides these existence results, Sperner's lemma is also used to establish an impossibility result, the Monsky theorem. Because of the wonderful applications of Sperner's lemma, it is very interesting to study if we can find a rainbow simplex efficiently. So in the computational problem for simplicity, we consider the Coulomb triangulation with a side length of epsilon equaling 2 to the minus n. The figure on the right presents a Coulomb triangulation for the two-dimensional standard K-simplex, two-dimensional standard simplex in which each small triangle is equilateral with a side length of epsilon. As each point in this triangulation can be uniquely represented by roughly kn bits, we can consider that the coloring is given by a polynomial size circuit C. Our task is then finding a small rainbow simplex in the triangulation. Here, a trivial algorithm is to enumerate all the small simplexes, but it has an exponential time complexity. According to previous work, this is conjectured to be roughly the optimal. The computational complexity of k-dimensional Sperner is PPAD complete. Well, PPAD is a class of all total NP search problems that can be reduced in polynomial time to the end-of-line problem, which is conjectured to have an exponential time complexity. In end-of-line, we are given an exponential size directed graph by a polynomial size circuit. In the graph, each node has an in degree and an out degree at most 1. And we know here there is a trivial source. So there always exists some sink in the graph. Then the task is to find a sink or another source, which are given by the red nodes in this example. it could be easy to see that if the graph is only given by a black box, we need an exponential number of queries to find such a solution. As mentioned earlier, there is a polynomial time reduction from Sperner to this end-of-line problem. The query complexity of the Sperner problem can be shown to be exponential. In our work, we consider the following relaxation of the problem. Instead of finding a rainbow simplex that contains all the k+1 colors, we are now only wanting a trichromatic one. Or equivalently, we want to find a small triangle in the triangulation that is colored by 3 different colors. We call this problem 3 out of k+1 approximate Sperner, or for short, approximate Sperner. We will call the original Sperner problem the exact Sperner problem in this talk. The main result of the paper is that this relaxation remains PPAD complete and has an exponential query complexity for any constant k. So any constant k greater than 2. Next, I will present our applications in n-way-free k-cutting, which is one of the most important problems in the literature of file division. In the n-way-free k-cutting problem, the cake is abstracted to an interval, say 0 to 1. We want to cut the cake into k+1 pieces and then allocate all these k+1 pieces to n agents, where each agent can get a disjoint but non-empty subset of the pieces. We say the agents all get connected pieces if the number of agents and the number of pieces are equal. That is, n equal to k+1. For the agents, we consider the following general preference utility in our work. In this setting, we have a utility for each agent, each cut, and each piece in the cut. If an agent gets a bundle of multiple pieces, the utility is the sum of the single pieces inside the bundle. To ensure the existence of file k-cutting, we make the following 2 mild assumptions about the utility function. First, we assume that the utility function is Lipschitz. That is, 2 cuts do not have significantly different utilities on their pieces if their cut positions are very similar. Second, we assume that any empty piece has a utility of 0, while any non-empty piece has a non-zero utility. The finest concept we consider is n-way freeness. We say that agent I is epsilon approximately n-way free if the utility of his or her bundle Bi is epsilon approximately greater than any other agent J's bundle under agent I's utility function. We see that a k-cut scheme consisting of the cut positions and the allocations is epsilon approximately n-way free if each agent is epsilon approximately n-way free. When epsilon equals 0, we say that it is exact n-way free. Earlier works have shown that there always exists an exact n-way free k-cut with connected pieces for any number of agents. But the computational complexity of finding such k-cut is PPAD complete and has a poly 1/epsilon query complexity. In our work, we further consider the setting where we allow more cuts and require fewer agents to be approximately n-way free. This is the relaxation of the earlier hard problem. When we allow more cuts, we need to more carefully deal with the overlapping cuts, which may induce some equivalent cuts, but the cuts may be different. For example, cutting at positions 0 and 0.5 induce the same set of non-zero pieces as cutting at positions 0.5 and 1. But for these 2 different cuts, the utilities of the pieces should be equivalent. That is, they should be equal up to a permutation. So we need our general preference utility function to satisfy this equivalence. Formally, we say a k-cut is p out of n way free if there are at least p approximately n way free agents in the k-cut scheme. Our result is that even 3 out of n way free k-cuts are PPAD complete to find, and they require a Corey complexity of poly 1 over epsilon. We establish this result by a reduction from approximate Sperner, and the reduction is quite simple. First, we can transform any k-cut into a point on the k-simplex by the sizes of the pieces. Then, for each cut, if the corresponding point on the k-simplex is a vertex of a small simplex in the triangulation, we just let the piece corresponding to the color of the point have a utility significantly greater than 0, while letting other pieces have approximately 0 utility. Then we interpolate inside each small simplex. In this way, any 3 out of n way free k-cut can imply a trichromatic triangle in the Sperner's coloring. And so we get the reduction from approximate Sperner to this k-cutting setting. To ensure that the utility satisfies the earlier mentioned equivalent cut property, we need the Sperner's coloring to satisfy some symmetry, where the coloring on every d-dimensional facets should be identical up to a permutation of the colors. Our construction of the hard instances of approximate Sperner can satisfy this symmetry. Besides the general preference utility, the utility functions are also studied in the literature. A more popular way to model the utility of a piece is to only use its left and the right boundaries, which is independent of other irrelevant cuts about cut positions for this piece. To distinguish this kind of utilities from the general preference utilities, we call them valuations. We say a valuation is additive if the utility function is an additive function. For additive valuations, previous works have shown algorithms that find an epsilon approximately n way free k-cut with connected pieces with a polylog 1 over epsilon queries for 4 agents. Also, it is impossible to find the exact n way free k-cut with connected pieces using a finite number of queries if there are 3 or more agents. Further, if we allow each agent to get multiple disconnected pieces, Arthur and McKinsey have shown an algorithm using a finite number of queries. The later two result is based on a Robson-Webb model for n way free k-cutting. On the other hand, for general valuations, the problem is easy for 2 agents, but hard for 4 agents. It is still open for 3 agents. Next, I will talk about the techniques we use to prove the hardness of approximate Sperner. Our reduction is one step from 2D Sperner to 3 out of k plus 1 approximate Sperner, where the 2D Sperner instance have a triangulation side length of 2 to the minus n, while the approximate Sperner instance has a much smaller triangulation side length, say 2 to the 4kn. Also, we consider continuous instances where we color the entire simplex, and the objective becomes to find 3 differently colored points that are close to each other in the simplex. A very simple attempt for this reduction is based on a recursive construction in which we can establish the PPAD hardness of the exact Sperner. problem. Suppose we have a hard k-1 dimensional instance. To construct a k-dimensional instance, we can simply put the k-1 dimensional instance near the bottom of the k-simplex, and then use the new color k+1 for the remaining part of the k-simplex. The PPAD hardness of exact Sperner follows the argument that if we have a rainbow simplex in the k-dimensional instance, its projection to the bottom k-1 simplex is a solution for the k-1 dimensional instance. However, this construction does not work for our relaxation, even for the 3 out of 4 approximate Sperner problem, because we have a lot of trivial color switches on the bottom 2-dimensional instance. I suppose this is the bottom 2 simplex in a 3-dimensional instance. Though it is hard to find a rainbow triangle in it, we can easily find a point whose neighborhood is colored with both blue and red. And this kind of point can be simplified by binary search. We see such a point, a color switch. In our simple attempt, we will put both red and blue colors near the neighborhood of this point and then switch to the fourth color green on top of it. This coloring simply induces a trichromatic triangle on top of the color switch, which could be easy to find. To resolve this issue, the main idea is that we can put a standing copy of the hard instances on top of the neighborhood of each color switch. And technically, we assume that the 2D instances have a good bottom boundary, having half of the boundary colored by blue and the other half colored by red. To define the neighborhood of the color switch, we first ignore the trichromatic regions on the bottom 2D instance because they are PPAD hard to find. Then the color switches are shown by the dashed lines in both figures. The neighborhood is then defined as a set of points that are within a much smaller distance than epsilon to these color switches, which are shown by the transparent regions. Then we can continuously define a converted coordinates for this point inside the neighborhood. The sources of the dark blue arrows are points with the converted coordinates of 0, and the sinks of these dark blue arrows are points with the converted coordinates of 1. Using these continuous converted coordinates and the new coordinates in the 3-dimensional instance, we have enough number of coordinates to put a shrunk copy of the base 2-dimensional hard instance on top of each neighborhood. Here we need to modify the color of the base instance according to the color in each color switch. For example, the instance on top of a blue-red color switch should consist of blue, red, and green, while the instance on top of a red-white color switch should use red to replace the blue and use white to replace the red. Finally, for points that are not in any neighborhood of color switches, we use the method in our simple attempt to ensure that there's no spurious solutions. And this figure concludes how we construct the hard 3 out of 4 approximate Sperner instances. For higher dimensions, we continue to use a recursive construction. Consider we add the coordinates of the k-simplex 1 by 1 into our construction. At the same time, we maintain a 2D projection Y and a palette C of 3 colors. For the instance, the capital CY color in the palette is then the output color of the k-dimensional instance. where this capital C refers to the unmodified coloring in the base two-dimensional instance. To lift from a k-dimensional instance to a k+1 dimensional instance, we can similarly compute the converted coordinates and keep track of the colors inside the neighborhood of the color switch. And the final ingredient of our construction is to ensure the symmetry we need for n-way free k-cutting. It turns out that we only need our converted coordinate to satisfy this additional property on the bottom boundary. To do so, we can simply use interpolations. The main takeaway message of this talk is that finding a trichromatic simplex in a k-dimensional Sperner's coloring is no easier than finding a rainbow one. It is still PPAD complete. As an application, we show n-way free k-cutting is still PPAD hard under the general preference utility function, even if we have more cuts and only ask fewer agents to be n-way free. After our work, the n-way free k-cutting problem is still open under other utility functions. For general evaluations, we don't know the complexity of 3 agents or with more cuts and fewer n-way free agents. Another major open problem in this literature is the complexity for 5 or more agents under the additive or more generally the monotone evaluations. My talk is over. Thanks for listening. The following 2 pages are the references.